Yes. And let me, we have to wait for a few seconds because until the email arrives to everyone, you know, it has to, it takes a few seconds. So it's not.
Okay, now we are in internet. I will put the link if you like to check anyway. So let me 1 second put this in the chat. Not where's the chat is here. Okay, so I will send all this, the link to all the community of physics. I prepare an email for that.
It's like
Okay. One second more and we'll start. Okay, now we can start if you like, Luis.
Yes, great. So just a second. So I'm checking that everything is going live. Just a second. Yeah, now we are. Okay, so buenos días a todos, bienvenidos a esta defensa de tesis de Gregorio González. Since we have, dado que tenemos miembros externos, voy a cambiar a inglés. So hello to everybody, welcome to this PhD defense. I'm really happy to be here representing the academic committee of the postgraduate program in physics of the University of Chile. Gregorio Gonzalez is going to defend today his thesis titled Dissipative Structures Formation in Liquid Crystals. And we are very happy to have here Professor Stefania Residori, Professor Sylvain Barbey, Mario Wilson, Dr. Mario Wilson, Professor Paulina Hidalgo, Professor Alejandro Valdivia, who is formally the president of this examination committee, and Professor Marcel Clark, who is the advisor from Gregorio. And so it's really a pleasure to welcome you all. I will just explain very briefly how this goes. Usually we'll have the presentation about 45 minutes, so try to be right in time, Gregorio. Then we will have a session of questions and answers. Typically, this is moderated by the president of the examination committee. And then there will be, usually there's also a space for questions from other questions that might have been put in the chat. And then we'll have a time for deliberation and the final decision on this thesis. So welcome to everybody, and Gregorio, the floor is all yours now.
Thanks, Luis.
Only one comment, Luis. Maybe if some person like to ask questions for the YouTube, they can. I can read after when we finish the committee question.
Yes, yes, indeed, to replace what is usual in person defense. Yes.
Do I start? Okay. Hello, everyone, and thanks for being in my thesis defense for obtaining a PhD in physics. I'm Gregorio Gonzalez Cortes, and I will talk about dissipative structure in liquid crystal, which is my dissertation topic. I'm a student from the Facultad de Ciencias Físicas y Matemáticas of the Universidad de Chile. And as the title shows, all this presentation will revolve around the liquid crystal physics. So for starters, what is liquid crystals? Liquid crystal is a state of matter which correspond to first described and observed, properly observed by Frederick Reinitzer. And he observed in cholesterol benzoate that if you are at room temperature and you keep increasing when you are at room temperature, the cholesterol benzoate is a solid, is a powder, a white powder. If you increase the temperature beyond 145 degrees Celsius, you reach the melting point in which this solid transforms into this opalescent liquid. But if you keep further increasing the temperature beyond 178 degrees Celsius, you have a clearing point, a second phase transition, which corresponds to the phase transition happening between this opalescent fluid and this transparent fluid. Now, from a chemistry point of view, there are multiple kinds of liquid crystal. This test, we will focus mostly on calamitic liquid crystals. Calamitic liquid crystals correspond to this general structure in which we have two aromatic rings with a linkage group and two moieties in the extremes. This is called the rigid part, and this is called the flexible part. And the presence of these two elements give us this property of having this opalescent state and the translucent one for higher temperatures. Now, from an order point of view and a order parameter point of view, what we have is that when the cholesterol benzoate or any liquid crystal is a solid, any calamity liquid crystal is a solid, all the matter is well ordered both positionally and orientationally. Indeed, these roads, calamity means road, these roads are well ordered and all point in the same direction. When we pass the melting point, we lose the positional ordering. Indeed, all the molecules point in any are in any arbitrary position, but we still have a orientational order. Most of the molecule or all the molecules point more or less in the same direction, not exactly in the same direction, but more or less in the same direction. And if you keep further increasing the temperature, you lose both a positional and orientational order, which is called isotropic liquid. Now, how can we detect this phase of matter? For this, we use polarized optical microscopy. So what we do is we illuminate a liquid crystal sample with polarized light, and we observe with a cross polarizer called the analyzer. So if the matter is birefringent, we might have a bright matter, bright state. And if the matter is completely isotropic, we will have a black state. Indeed, in this sample, we are increasing the temperature, so we pass and we observe the emergence of these dark bubbles in this sea of bright material. The bright material corresponds to the birefringent material, which is the nematic liquid crystal, and the dark state corresponds to the isotropic liquid. Now, the order in liquid crystal can be controlled by several mechanisms. To name some few important examples, we have a temperature. Indeed, we can have in cholesterol liquid crystal the spontaneous emergence of this pattern and finger formation. Also, liquid crystals are very nonlinear material from optical point of view, so we can have the propagation of solitons of light called nematicons, which are the result of a balance between the nonlinear interaction of the light with the medium and the diffraction, which creates a solitonic propagation of light. Also, we have, for example, the magnetic case, in which we have a magnetic material ring in the outermost region. And due to the interaction of the liquid crystal with the external magnetic field, we have that the system self-organized to create these vortices states. These triplet of vortices is the solution. And vortices is also a very robust solution that we can find in several physical contexts. And lastly, maybe one of the most relevant and important examples correspond to the electric field. What we have here is a microscope objective, and we are seeing here the pixels in a liquid crystal display. Indeed, it's a LCD screen, which is the one that most of us are using to see the presentation that I'm giving. And indeed, we apply an electric field. This electric field controls the intensity of light that is transmitted from each pixel. There are several other mechanisms, but this is a good overview of the possible mechanism to create this control of the order. So when we talk of order, we need to define a order parameter. So we need to see which kind of symmetries has this material. The first one is that the calamitic matter can distinguish between top and down. This rows has no top nor bottom. So any theory will have to consider the symmetry between n and minus n, being n the average direction in which this matter is pointing. So for this, we define this tensorial order parameter, which we divide in two components, the scalar order parameter and the orientational part of the order parameter. The scalar order parameter is just a measurement of how order is the matter around the director. Indeed, we define theta as the angle between the average and each one of these differential volume. And we compute with this Legendre polynomial, and we take the average over an ensemble. We will obtain that when all the matter is completely ordered, namely all the rows point in the same direction, we have that the scalar order parameter is 1. And when we decrease the order and the matter start to have more degrees of freedom, we have decrements of the S order parameter, the scalar order parameter. And indeed, when the matter is completely disordered or all the molecules point in any arbitrary random direction, we have that S is equal to 0. Now, as I said, electric fields are a very important control mechanism of order, and is the one that we will use during a good part of this presentation. So to understand the interaction between external electric fields and the liquid crystal matter, we can, for example, study the torque that exerts an external electric field over the liquid crystal. And indeed, the torque is given by the cross product of the polarization of the material and the external electric field. And if we consider that the susceptibility tensor, permittivity tensor, inherits the properties of the tensorial order parameter, and we can compute the torque, and we obtain this expression. Now we have that the torque that is exerted will depend on this constant, which is called the electrical anisotropy. And during this presentation, we will focus in the case where the electrical anisotropy is positive. There are materials where it's negative, but we will not discuss this in this presentation. And the end result is that the torque will try to align the external electric field and the director of the liquid crystal. Indeed, we can obtain the same conclusion if we study the energy. This is the energy stored by the liquid crystal under an external electric field, and we obtain the free energy related to the electric field. And consider that this is a constant part under a constant electric field, we have that the energy will be minimized when n is parallel to E. So it's basically the same conclusion. The torque will try to align the matter with the director with the electric field, and the minimum of the energy will be when the n is collinear with the external electric field. Now we should consider the experimental setup that we will study in concrete. Indeed, for this, we use a plain capacitor filled with a liquid crystal. The liquid crystal is the electric medium. And we perform a Rubin treatment to fix the boundary conditions to be parallel to the plates and parallel between both plates. And we apply an external electric field. By applying an external electric field, and it's a plain capacitor, so we have that the external electrical field is this expression, where B is the applied voltage and D is the distance separating the plates. We compute the energy as the competence between the elastic energy, which in the approximation of that all the deformation modes have the same strength, and the electric energy. And if we perform a minimization of the free energy, we obtain this elliptical integral. It can be easily solved by numerical means. But if we do an expansion near to the threshold where the matter starts to reorient, we obtain that we have non-zero solutions, namely that all the molecules will rotate and will not have a zero angle. Only above certain voltage called the Frederick voltage, which is a threshold over which we apply a voltage that is beyond that point, we will start having molecular orientation. And indeed, for example, here we have a liquid crystal cell filled with liquid crystal. This darker region is where the transparent conductor is placed. So this region will be under the influence of the external electric field, and this region will not. And when we apply an external voltage, we observe a complete reorientation of the liquid crystal. The liquid crystal, now it's in the dark state, is parallel to the direction of the propagation of light. So there is an isotropy from the light polarization point of view. So we see a dark state under cross polarization. And then when we turn off the voltage, we return to the normal state. Now, in concrete, the device that I use is correspond to this is a mirror. So we inject light, it's reflected, and this can allow us to sample the refrangions of the material inside. And we apply the external electrical field, but in addition to that, we place a photoconductive layer in which we can apply an external light illumination, which may or may not be spatially structured. And the effective voltage applied will be the external voltage applied by the generator, and the illumination applied. And in concrete, we obtain this setup, which corresponds to the liquid crystal light bulb placed in an optical loop. Here we have an SLM to place some mask and to control the injection. Polarized beam splitter, which allows us to use polarized light. And here we see that the light crosses and goes back and forth. We have a 4F lens arrangement. So in this plane, we have the same image corresponding to this plane on the liquid crystal light bulb. And we use an optical fiber bundle to transmit the illumination over the liquid crystal light bulb to the photoconductive layer. So effectively, we have a system in which the liquid crystal light bulb interacts with itself through the light applied to the photoconductive layer. This system has been studied previously, and it has a very wide possibility of phenomenology. For example, we have patterns and hexagon and p-hexagons from sharper or more softer transition. We have more complex structures, for example, quasicrystals, solidonic structures, and orientational fronts connected to orientation of the liquid crystal. One of the topics during my PhD was fronts, orientational front propagation, and speed control of the fronts. And due to time constraint, I will not be able to get very deep into this topic, but the two main results correspond to the control on the propagation speed of the fronts by modulating the landscape in which the front propagates. So we have two here, two fronts, one propagating in plain non-oscillatory landscape. And here we have one propagating an oscillatory landscape, and both have the same intensity, light intensity. But due to the spatial structuring of the light, we see different velocity in the propagation speed. And also, we obtain the control of, to some degree, of the front speed by using the non-variational terms, non-variational dynamics, that applies the diffraction of the light over the photoconductive layer. And indeed, we can achieve some degree of control of the propagation speed up to a certain limit. The other main topic during my PhD was pattern formation and pattern dynamics. So here we have 3 examples of patterns. This is a liquid crystal, polyester liquid crystal. Here we have a Rayleigh-Benard cell in which there is a fluid under a temperature gradient. And here we have a satellite image of a forest in which all of these 3 situations, the matters self-organized, creating a well-defined wavelength structures. In this case, for example, the dark regions correspond to vegetation, and the bright regions correspond to soil. So we can see that it's quite robust as a phenomenon. We can see it in very wide and different scales, and in very wide and different physical contexts. Now, patterns can be complex. For example, here we have Belousov-Zhabotinsky chemical reaction. And if we increase the concentration of one of the reactants involving the chemical reaction, we can see a transition from this very regular spiral pattern to a more complex and rich structures. And the same can be seen in Rayleigh-Benard convection cells when we tilt the cell. So the gradient is not collinear with the gravity. And we can observe that there is an emergence of patches of complexity in the time evolution of these of the patterns that are generated in both cases. So indeed, we see a very rich phenomenology. Now, as I showed previously, in the liquid crystal light bulb is possible to obtain patterns. Here, for example, we have one-dimensional, two-dimensional cases, and they are dynamic. Indeed, we see the pattern and a constant creation and destruction of dislocation in these patterns. In the spatiotemporal diagrams, we can observe that when increasing the voltage, we pass from regions where we have a very stable and dynamic-less patterns. By further increasing the voltage, we observe a region where a more complex and not very well-defined wavelength rises. And if we keep further increasing, we return back to a more tamer situation where, again, we have a more or less well-defined wavelength or multiple wavelength, and not such complex dynamic as in the previous case. So the complexity is not monotonic with voltage. And indeed, we can observe that for the previous cases that I showed, we have a very well-defined wave number, spatial wave number. When we increase the voltage and we arrive to the more complex scenario, we have no clear and well-defined spatial frequency. And by further increasing, we have several wavelengths as we were able to see. And indeed, since we have patterns, we have that most of the dynamic is in the direction of orthogonal to the rows. And in the other direction, there is not really a lot of relevant dynamics. Most of the dynamics is in this plane. So it's the plane that we will focus on. We can measure the largest Lyapunov exponent by changing the voltage. And indeed, by measuring the largest Lyapunov exponent, which is a measurements of the predictability of the system. We obtained that for the more tamer region where the patterns are static, we have the largest Lyapunov exponent is negative. So we have a complete predictability over the system. But by further increasing, we arrive to these regions where the largest Lyapunov exponent is positive and very well defined positive over all the region, which correspond to the situation where the illumination is close to the dark state due to the self-interaction of the liquid crystal light bulb with it. And also we have this intermittent region where the largest Lyapunov exponent also varies a lot, sometimes is even negative. So we have a very rich dynamical scenario. Also, we can study from a statistical point of view. For example, we can study the emergence of extreme events. And extreme events are defined as events that are well above all the statistics that the time series of the system presents. For example, here is the elevation of the sea in some region of the Northern Sea. And we see that the waves are mostly in, all the waves are mostly in this elevation of 5 meters. And out of nowhere, it emerges a 20 meters wave, which is called rough wave in the context of oceanography. And we can observe that in a survey conducted over 30 years, they are very frequent. Consider all the places that we're measuring. So a lot of more of these events happening in places where no measurements was being performed. So these events are quite more frequent than one will expect. In optics, we can see this in several contexts. For example, in glass fibers, we can propagate light, and by the interaction of the different modes, we can obtain, indeed, by applying small deformations, the emergence of extreme events, which can end up damaging, for example, the optical fiber. And in other contexts, the semiconductor laser, we can observe that when we are slightly above the pump threshold in which the laser started to lasing to emit light, we have very few extreme events. But by further increasing the pumping, we observe a abrupt increasement of these extreme events, of these high intensity events. But again, if we keep further increasing, we arrive back to this tamer situation where the amount of extreme events decreases again. Now, in the context of the liquid crystal light bulb, we measure the proportion of extreme events and the excess of kurtosis, which is a proxy also of the amount of extreme events. And we can see that in the windows of the transition of these different states, we see an increment on the proportion of extreme events, which strengthens the hypothesis that one route to generate extreme events is by generated a transition between different states in any context. So every time that we have a transition, for example, here from the chaotic scenario to this intermittent scenario, we will see an increment, an abrupt increment in the proportion of extreme events. For example, here we have a probability density function measured for one of these cases. This is for this very high peak here. And we see that a lot of these events correspond to extreme events. Also, we can see that they are very well distributed over the liquid crystal texture. So it's not because there is some heterogeneity in the liquid crystal light bulb, for example, some glass bead or some dust that could focus some additional light. But this is due to the very well distribution of the extreme events. We claim that it's due to the self-interaction and the complexity of the texture, of the pattern texture that emerge in our experiment. Now, up to this point, we have discussed the measurements and properties of the texture that we observe, but we haven't discussed any mechanism. So one mechanism that we propose is the effects of misalignments in an optical setup. Indeed, here we can control and introduce an artificial misalignment by moving the plane in which this the optical fiber bundle is placed, so it's not really collinear with this line, creating a shift in space of the self-interaction. And indeed, we can see that when the system is well aligned, we see almost no dynamics. This is a movie, it's plain. And by further increasing the misalignment in the system, we see that it emerges some advection, as we can see here. And by further increasing, we start to see more complex scenario where more interaction can be observed. And in a very misalignment system, we see a very complex dynamics where we see this bright spots propagating in counterflow. So indeed, we have that this misalignment is in a self-interactive system, is a mechanism to generate patterns, but also to generate complexity in the pattern dynamics. And indeed, we can model this with a Swift-Hohenberg equation, which is the most simple equation that presents the pattern formation. But with the modification that the field is not, the evolution of the field is not given by itself, but it's given by a translation of itself. And we can compute the amplitude to obtain the relevant features and not the short wavelength structure. And we can see the numerical pattern dynamics obtained for this simple model. And we can see indeed the pattern formation under no misalignment. When we increase the misalignment, we see that the patterns start to advect. And by further increasing the misalignment, we can see the emergence of this complex structure, this spatiotemporal intermittency. And if we keep further increasing the misalignment and tune a little bit the parameter, we can observe this defect turbulence where we can see a constant creation and annihilation and destruction of these zero amplitude regions. So this very simple model, a very minimal model, can give rise to this very complex dynamics. And indeed, we can compute the bifurcation diagram, the phase diagram, and we can see that some of the observed phenomenology is related to the complex Gimbel-Landau equation. And indeed, we can see homogeneous steady state corresponding to the stationary rolls, traveling waves corresponding to the advected rolls, the spatiotemporal region, that is this one, and the defect turbulence. And all these secondary curves are related to the transition and some additional features of the complex Gimbel-Landau equation. Indeed, if we try to do some comparison with the experiments, we can see that we need to set a proper boundary conditions and a proper size of the simulation space, because in the experiment we don't have a very wide and very high number of patterns of maximum. So by taking this consideration, we obtain that in the numerical case, we obtain a power law in the spectral distribution of wavelength. And indeed, we obtain a critical exponent of -6. And in the experimental case, we obtain a critical exponent of around -2 in this region, which could give us some insight of how the scale should be to do some proper comparison between this very simple model, which is not really a numerical or a derived from free principle in the liquid crystal light bulb. But still, thanks to this, we can get some insight of the kind of scalement that the system requires. Now, an additional topic that I studied during my PhD is related to phototropic phase transitions. So as we saw previously, we can trigger phase transitions by changing the temperature in the liquid crystal. And this is very well described by the Landau-de Gennes model, in which we set an expansion of the free energy over the scalar order parameter, or the full order parameter, and if we fix constant the director, we obtain this model for the scalar order parameter. And when we do the evaluation, we obtain this, which corresponds to a multi-stable model, in which we have for some region of parameters, two equilibriums, which correspond to the isotropic states. The zero is always a solution, so we have that the S equals 0 is solution, the isotropic state, and a non-zero solution, which correspond to the nematic state. So how can we replace the temperature with the light? One mechanism is by considering the introduction of azo dyes into the mixture, in the liquid crystal mixture. So azo dyes correspond to these molecules, which has this azo bond, which has this photoisomerization mechanism, in which we have this molecule, we have this axis of symmetry, and these two rings are opposite of this axis of symmetry. And when we irradiate the system, we have that both of these benzenic rings are in the same plane, semi-plane, given by this axis of symmetry given by the azo bond. So this can be understood as a transition from a rod-like state and to a more boomerang-like shape state. And we can obtain a right equation for the concentration of the cis state, which will be the most relevant because the trans state is the basal state. The system will, if we wait enough time, all the system will be in the trans state. When we illuminate, we rise it to the excited state, and we obtain some cis state that will decay back spontaneously. So the concentration of cis state will be given by basically the light intensity to which the sample is subjected, and diffusion. So for this, we can see that the reason that we choose the green light is because we have in the laboratory a green light source, but any green light that is strong enough to trigger because all of this region can have this photoisomerization state. But here we have the maximum, and if we are close enough in frequency to the maximum in the wavelength, we can trigger the photoisomerization process. So since the laser that we are using is not in the maximum of the absorption spectrum, we will need a very strong pumping to obtain this phenology compared with the central wave. So experimentally, what we observe correspond to this propagation of this texture. This corresponds to a dark state, which is under cross polarization corresponding to isotropic phase, isotropic liquid. And when we increase the illumination, we see that it's invading this bright state corresponding to nematic liquid crystal. So indeed, we have a phototropic phase transition in which the isotropic liquid is invading the birefringent liquid purely by optical means. Also, phototropic transition has been observed in several contexts. For example, in molecules that have chemical reaction with itself, we obtain the same result or the same analogy, in which now the light acts as a mechanism to order the matter. Here we have a isotropic phase. We irradiate the system and we obtain a nematic state, and we turn off the light and we obtain back the anisotropic state. And we can have the same for several different textures. And also we can have the mechanism not in a liquid crystal dye-doped mixture, but in the case where the liquid crystal itself is a dye, has an azo bond, and we can observe a soliton propagation in this case. We can enhance the soliton propagation by considering this. So we're interested in the spatial properties of this system. So for this, we propose this model in which we couple the Landau-Degenn rate equation for the scalar of the parameter of the liquid crystal, and for the dye concentration. And the couple is given by considering that when the system is very well ordered, it's more difficult to the cis concentration to increase because the returning mechanism is innate. And also we consider that the scalar of the parameter decreases when we increase the concentration of cis molecule. And also we have to preserve the symmetries of this liquid crystal equation. And if we consider a cross transport given by the Onsager relations, we can obtain this pair of differential equation. Now, to get some insight of this in this model, we can consider that the cis evolution corresponds to a quantum process. So it will achieve the equilibrium very fast compared with the scalar of the parameter, which is a elastic process. So we can perform an adiabatic elimination, and if we replace the concentration back in this equation, we obtain this simplified model, which corresponds to the Sweet-Hockenberg equation. So we expect in this system, in the dye-doped liquid crystal cells, to observe pattern formation. And indeed, experimentally, we observe them. So here we have a comparison between the experimental texture measuring this setup under a twist boundary condition. And here we have a numerical simulation of the previous model. And by performing the stability analysis, we can observe indeed that we have a Turing stability in which we have a certain wavelength which is favored when we change the parameter of the system. An additional direction in which we move is by changing the dye. We are not using the commercial methyl red dye, but changing with this methyl red methyl ester, in which we change just this link. Now, by changing this part, we shifted the absorption wavelength. Now the green laser that we previously used as a pumping now acts, it doesn't perform any reorientation of the system. So we introduce a secondary laser, blue laser, to pump the system. And effectively, with this, we can uncouple the illumination, which is given now by the green laser, the probing mechanism, and the injection mechanism given by the blue laser. And with the help of the Craig mirror, we can subtract the effects of the blue laser, and we can just observe and probe the order parameter in the liquid crystal cell. And in this, indeed, in this model, we can observe these saturation mechanics. And from the spatial phenomenology point of view, we observe the emergence of rings, as we can see in the spatial temporal diagram. And for this, to model this, we use the same couple model as previously shown, but now we consider that the distribution of the light intensity is relevant because now the size of the pumping, the laser pumping, is very relevant to the scale of the physical experiment or the wavelength in which the system is developing. And it arises in additional non-variational term. And indeed, the simulation has very good agreement with the experimental observation. And an additional observed phenomenology that we measure corresponds to this finger propagation in the liquid crystal experiment, in the phototropic transition experiment, in which we observe the emergence of this finger texture that, when reaches the maximum radius that the light can sustain an isotropic phase, it stops and ends up in this circular shape. Now, if we start tracking the boundary of the propagation, we observe that we can detect 4 very characteristic regions. One of the rapid growth of several bubbles. So we don't have any characteristic circle. In addition, then we have a rapid finger growth region. Then a saturation in which the finger reached the maximum illumination zone where the light can no longer sustain an isotropic phase. And then the space between the fingers try to reach the same point. And then no further dynamics is observed because all the system reached the maximum radius that is compatible. When we study the wavelength versus the laser power, we observe a power law. The critical exponent in this power law that we measure correspond to around -3. So this can give us some insight of the kind of scaling that we could require to model this as a Huffman-Taylor instability, in which the critical exponent corresponds to -1/2. So we claim that indeed we have some kind of immiscible invasion of the isotropic liquid over the nematic liquid. But to model this, we recur to a more simple distable model, in which the only consideration that we made is that we propose an isotropic an unbalance between the radial diffusion. Here we have a Sweet-Hockenberg equation, and we have an imbalance between the radial diffusion and the angular diffusion. And by only considering this and imposing an additional constraints related to the growth of wavelength of patterns in the liquid crystal texture, we obtain a very similar phenomenology where we see a rapid finger growth that reaches a maximum radius, and then the space between the fingers start shrinking until they reach this maximum circle that is compatible with the illumination. By studying the phase diagram, we observe this phenomenology for low anisotropy. We obtain this ring texture, which has been observed experimentally also in liquid crystal experiments, in phototropic isomerization liquid crystal experiments. The finger propagation was the focus of this study, and also this homogeneous circle propagation of a circle, which also has been observed. And we observed this 3 phenomenology in this very simple model, which we weren't expecting to observe all this phenomenology that is observed in liquid crystal in this very simple and minimal model. So as a conclusion to my work, I want to do a very brief overview in which we were focusing in the interaction of matter with light and how to control the propagation dynamics of the liquid crystal with light. And indeed, we were able to control fraud speed propagation in liquid crystal devices. Also, we were able to control the complexity in the pattern forming in liquid crystal device, in the liquid crystal light bulb, and also propose a mechanism for generation of complexity in pattern formation. And also, I studied phototropic liquid crystal transition by using dye, and we were able to derive very simple yet effective models for these liquid crystal transitions. And I want to acknowledge CONICET and Miro for to finance my PhD studies, and also to Marcel and all the professors and colleagues in the LAFER group in which I performed my PhD thesis. Thanks.
Thank you very much, Gregorio. Excellent presentation. I guess we should go now to the questions by the committee. So, Stefania.
Gregorio, first of all, let me congratulate for the excellent work that you have presented to us.
Thanks.
And outstanding results, really. And for the excellent presentation, very clear and pedagogical presentation. So I'd like to ask some questions. I'd like to start with a general question, because you have presented us rich dynamics, dynamical behaviors and patterns in liquid crystals, and different type of structures of coherent structure, like localized states, pneumaticons, vortex, log waves, fingers. So could you give us general comments on which are analogy, similarity, and difference between all these types of structures?
All these different structures are dissipative structures and are very common in matter, and are a result of the balance between the injection of energy and the mechanism of dissipation. So basically, the matter tries to dissipate in the most efficient way the excess of energy that it has. So in the case of liquid crystal, of course, under different injection of mechanism, we will obtain several different mechanisms that the liquid crystal will try to self-organize in order to optimize some general quantity in the system. So, for example, the vortex formation is the result of a competition between the elasticity, which tries to maintain well-aligned all the liquid crystal, and we have a force that tries to push it outside of this direction. So the system will try to play in some mechanism, and the solution is a vortex. And for all this example, we have that the common feature is the existence of a dissipative mechanism, which is given in liquid crystal because it's a very viscous fluid in general. They are very viscous fluids, and the different injection mechanism. Indeed, as we saw, when we have no injection mechanism, when the liquid crystal cells were relaxed, for example, we obtain homogeneous textures with no dynamics, with no really interesting phenomenology. So I will say that the common link between all this phenomenology is the interaction of the injection of energy and how the system can relax all this excess.
Okay, thank you. Another question is about the role of boundary condition, anchoring conditions of the liquid crystal. So can you comment a little about this role? For instance, in the light valve.
Okay, yes. In the boundary conditions are maybe one of the most relevant aspects, because it will give us which is the expected phenomenology. Let me arrive to the simple. Okay. So, for example, the liquid crystal light bulb that we were using during my PhD consists in two planarly aligned layers. So, the only way that the system has to move on their homogeneous forcing will be to twist. The molecules will try to rotate to try to align or to reach the equilibrium between the electric force and the elasticity. But now, for example, by, for example, doing no rubbing or doing a deposition of silica, we can obtain homotropic boundary conditions in which the molecules are not in this parallel to the plate, but orthogonal. So they are like in this configuration. So now when we apply electric fields, and let's imagine that they have, for example, negative electric constant, so they will try to align or to be orthogonal to the applied electric field. the molecules will try to display like this. So we will obtain, for example, vortices. And indeed, I haven't worked with this kind of liquid crystal devices, but there are several works considering these boundary conditions, for example, to creation of vortices and vortices lattices. We recently acquired a liquid crystal light bulb with this boundary condition, but we haven't started to study it yet. We are yet to set up an optical setup to study what are the effects and see the analogies and different experiments that we can perform. But indeed, boundary conditions are very relevant for liquid crystal, and they will determine which texture we will obtain. If we will obtain vortices, if we will obtain front propagation, or some other configurations.
Yeah, sure. So it's very rich depending on whether you use which type of boundary condition, which type of injection of energy, as you said.
Yes.
Okay, so in this setup you have, yes.
Oh no, and that is at the end an interplay between the properties of the liquid crystal, the boundary conditions, and the forcing.
Sure, and also the geometrical configuration yourself, yes. Because for instance, in the nematicons, the light is propagating inside the slab of liquid crystal. So you can also play with the transfer and the longitudinal propagation of light. So it's very, very rich. So since you are in this slide, here you have used the L, is the free propagation length is negative, no? And so what does it change if you change L from one side of the other of the 2F configuration, negative, positive L? What does it change in the front propagation or in the localized structure?
Okay, so this free propagation length, first is called free propagation length because we have this 4F lens arrangement. So if we place the optical fiber bundle exactly in this plane, we will have no free propagation, and indeed the light that passes through this plane will be the same that passes through this plane because that's what happens when you have a 4F correlator, which correspond to two lenses well balanced. Now, if we are out of this plane, we will have that the propagation of light, the diffraction, will start to play a role because the light diffracts, and due to the diffraction, we have these focusing effects, and now this parallel wavefront here. So if we place it in a different position, we will have an excess or deficit of diffraction, and that is the free propagation length. So the main role that has in the dynamics is that it introduces non-variational terms. If we study the effect on the propagation of light that reaches the photoconductive layer, effectively it has a non-variational effect on the applied voltage. Will change the light distribution. That will change the voltage profile. That will change the liquid crystal distribution, and that will introduce, for example, permanent dynamics or other non-variational effects. In the most concrete case, here, for example, we have in the front propagation, when we have in the positive L free propagation length, we can control the propagation speed of the fronts. If we increase the L, the front start to propagate faster. But if we are in the negative region, the front doesn't change the speed. What the front does is it changes its shape and tries to maintain the same speed. So in this simple case of just trying to create a orientational fronts, we can observe this very heavy effect in which for positive L, we have control in the propagation in the speed, but for negative L, we have a control over the shape of the front, but we lose all the control over or we have no control. The speed remains the same. And in several other contexts, it will have another effect. For example, for negative L, you will have patterns, and for positive L, you will have more easily soliton structures. So it's not really, it will be very dependent on the precise experiment that you want to perform. But this simple case of front propagation, I think it's very clear that the free propagation length can have a very different behavior when you are in the positive diffraction, in the excess of diffraction, or in deficit of diffraction to achieve the 4F correlate.
Okay, and this has an influence on the localized structure, stability, and properties.
Yes, all the structure will be influenced because at the end, the free propagation introduces non-variational dynamics in the solutions. And non-variational dynamics can yield, for example, to permanent dynamics and so on.
Okay. So another question I'd like to ask about the slide 19 or 22, when you show the largest Lyapunov of exponent, we that there are some transition windows, like you call the transitions, where the dynamics suddenly change to another, and it is in these windows that you observe the most of the rock wave phenomena, actually.
Yes, we observe an increment on the amount of extreme events in these transitions. For example, here.
Okay, so how do you relate this? Is there, could we find a relation with the fact that when you have this transition, it is correspond something in this, when you look at the homogeneous steady state?
Sorry, the communication was interrupted a little bit, so
okay.
I couldn't hear completely the question.
So how can you relate this phenomena with the change of the dynamics, changing to you should have bistability regions. If you look at the steady state, homogeneous steady state, you have bistability regions that are connected. Okay. So can you give some hints on this?
Yes, in this particular experiment, we focused in controlling the voltage that we apply. So in this other studies, for example, in this for this mechanism of misalignment, what we studied was the misalignment. So it's not really the same parameter that we're moving. The voltage is more related, for example, to the epsilon parameter than to the delta parameter. So regarding the this particular slide and this particular experiment, these transitions are, for example, here we have a fully developed complexity, which correspond, for example, to defect turbulence or most possibly defect turbulence. And we pass to this window where we have a some sort of spatial temporal intermittence. So indeed, one could expect maybe as a proposal that if we perform, for example, numerical simulation of this equation, and we get close, for example, for this transition or this region, one could expect to see an increment or a bursting in the proportion of extreme events in the texture that we are obtaining. We haven't measured that, nor doing numerical simulation in that direction yet. But we're studying currently how to link exactly this result of the misalignment induced dynamics with the observed phenology, in particular the statistical components of the patterns in the liquid crystalline valve experiment. So I don't have a clear-cut answer, but as a proposal, I will say that this is related in the other model as that if you get closer to a region where we have any transition of complexity to a maybe less complex system or no complexity, you should expect to see a bursting in the proportion of extreme events.
Okay, and that's very interesting. That's very interesting. Yes, sure. Okay, so I don't want to take all the time. Just let me one last question about the last topic of the photoisomerization. So can you tell just briefly some possible applications of this kind of operation of the liquid crystal, if you have in mind something?
Yes, indeed. For example, in this configuration, what we tried to do was to sample. Let me change from pointer to pointer. To sample the order parameter in the liquid crystal cell with the green light and the changes induced by the blue light, the injection light. And we can sample that by checking the transmitted light. For example, here we have the bright state and it emerge the dark state and it emerge a brighter state, or will depend on the polarizer configuration. But this can be also thought as, okay, so I have an injection mechanism, a control mechanism that will change the birefringence of the liquid crystal, the dye-doped liquid crystal cell, and due to the interaction of the birefringence in the liquid crystal light cell, will change the effective transmittance of this light. So this could be understood if we could control this deposition or the profiling of this blue light, could be understood as a purely optical spatial light modulator. Indeed, the control of this deposition of this light is very easy because we have that for the green light, we have a transmittance. So if we tilt the mirror, we will see only small translations. But since it's a mirror for the injection, we'll see very sharp changes in the position of the light. So, because if we tilt, we can change this to this. So indeed, we can create some sort of a spatial light modulator operated by purely optical means, without the help of any thermal mechanism or electrical mechanism. It's purely optical. So that will be a direction in which you could apply this.
That's very nice. Yes, sure. It's very interesting, very promising. So thank you. It's okay for me.
Thank you. Thanks, Stephanie.
Okay, thank you very much, Stefania. Are you finished, right?
Yes, right. It's fine for me.
Yeah.
Okay.
Thank you very much, Stefania. Silvan?
Yes. So it's up to me. So yes, so Gregorio, I would like to first congratulate you for the impressive work that you have presented today and for the very nice presentation. Okay, so in your manuscript, there are a lot of results, obviously, and you couldn't show them in your presentation, but you succeeded, I think, to show a few highlights in your presentation, and I think it was a very good presentation with this respect, to give an idea of everything that you have done in many aspects of nonlinear science, working with fronts, pattern formation, extreme events, working with some chemistry part, optics. So you've dealt with a lot of subjects in your thesis. So obviously, I have also some questions to ask you. And first, I would like to come back to, so you didn't really mention that in depth, but to come back to the front speed. And in particular, so in your results, you have studied the difference between when you have front propagation in a unmodulated landscape and in a modulated landscape. So first of all, can you recall the main results? And after I will have a question for you about these results.
Okay, so basically the mechanism in which we trigger this, or which is the cause of this reorientation in the liquid crystal orientation, is by when we illuminate and it's reflected and it's retroinjected in the photoconductive layer, it creates it changes the landscape, and we have, for example, the transition from monostable, which is the only the dark state is the only equilibrium of the system, to, for example, this case in which now the dark state corresponds to an unstable equilibrium, and this illuminated zone and this bright state correspond to an stable equilibrium. So, for example, in this case, we have we claim that we have a Fischer-Kolmogorov-Petrovsky-Tikhonov front connecting an unstable state and a stable state. And the bifurcation parameter is given by the light intensity. So we set some voltage value near to the threshold, and we go over the threshold thanks to the light. Now, what happens when the light has a spatial profiling in this example? Well, in this example, we have shown that what you will have is that the average speed of the front will change, indeed it will increase, when you have this modulated landscape. So the light intensity on average of these two cases is the same. But due to the modulation and the nonlinear interaction between the modulation and the front itself, we have that the resultant average propagation speed is faster. Of course, the same argument could be extended, for example, to bistable fronts, which is also a result that is shown in this other work. And in that case, we observe the same kind of behavior. We have the pinning mechanism, which is natural and expected in situations where we have a wavelet. But also we can observe that we can control the propagation of speed or the rate of the increment of the speed by modulating the landscape or the forcing, which is exerting this transition from changing the relative stability of the two states, the dark and bright state, or that even can trigger the dark state to the unstable. So basically, as a whole or closed package, I will say that you can control the average speed propagation of fronts by using the same light intensity in total, but if you modulate it, you will obtain different propagation speed.
Okay, so to summarize, when you have modulated landscape, you have a higher average speed.
In the case of FKTP fronts, yes. In the case of normal fronts, basically it creates a pinning region. And
okay, so that's very interesting because it really looks like what's going on in excitable systems, where you have, for instance, in nerve cells, in neurons, you have excitable waves which goes faster when you have discrete cells than a continuous cell, let's say. So in your case, okay, you don't have discrete cells, you have modulated cells, but it's close, I think, to the case of a discrete propagation, no?
it could be modeled like that. For example, you can read the situation. If I understood, you have basically, for example, in the case of neurons, you have the cell and you have the myelin, and the myelin is modulated or something like that in the path. And you have a higher speed when you have this modulation in the myelin compared with the homogeneous tube of myelin.
Indeed.
So you can model that exactly as this, where you have that. The analogy will be that in this case, the myelin will be the amount of myelin, the non-partial section of the myelin, will be the bifurcation parameter. And by modulating the myelin, you will obtain effectively that you are modulating the parameter, which is a complete analogy if you have an unstable front, which is expected in excitable system, to this situation. So I will say that it could be modeled in this way. Of course, it will be needed to really check all the models and the internal mechanism to do the claim. But I will say that if you observe faster speed in the propagation, when you have modulation, I will say that that implies that the thickness of the myelin tube is some sort of proxy of the bifurcation parameter for these fronts. So I will say that the analogy, my bet will be that it's a good analogy.
And can you compare the situation between FKPP fronts and bistable fronts, for instance?
Yes. Let me check if. Okay. Let me check if I keep that slide. I'm almost sure. Okay. So, for example, here we have the complete model. Here we have the complete model that we use, which correspond to a cubic saturation nonlinearity. And we have that the magnification parameter is spatially modulated with a sinusoidal one. So basically, we have that in this model, we have this stable region where we have that the dark state, which corresponds to the 0, and the bright state, which corresponds to the upper branch. Is like that. And indeed, the stable range changes with when we increase the strength of the modulation. So that's one main result. The stability cycle gets increased when you consider this. So that will push the FKPP fronts toward higher intensities. Because the stability cycle is like okay. So now regarding to the speed, you will have that the main effects in the bistable fronts will be the emergence of a pinning zone. So in the homogeneous case, you will have that the speed will increase monotonically when you move the bifurcation parameter in following this red curve. But when you introduce the wane length, now the fronts get pinned because it has no stimulus to keep moving, because it has to overcome some nucleation barrier, some nucleation energy, which will create this scenario where you have a more robust range in which you have no propagation of light. That could or could be not desirable, but indeed that can give a mechanism, for example, to control the speed. For example, you can have that, to control the position of some fronts with this. Because in the non-modulated case, the 0 speed is a point. The 0 speed parameter is a point. So experimentally, it's very difficult to pin that point, to tune the peril to that point. So basically, you will have a very difficult time stopping a front, namely controlling the position of a particle that is being dragged by the front, for example. But when you have the modulation, this zero speed case, now it's a region, so you will expect it to be very robust, to be very achievable. So you will use this as a control mechanism of the position of something being dragged by a front. I don't have a really clear-cut analogy in my mind right now. But for example, if we consider the position of the front as the particle, we can control the position of that, which is experimentally not really possible in the continuous case. And in the case of FKPP fronts, since the lower state is unstable, you will have always a propagation of the front. So indeed, in the case of FKPP fronts, you can now have this complete full rich scenario of no velocity, and you will always have propagation from the unstable state to the stable state, except in some very high weird cases of high codimension. So I will say that that's the main contrast. You will have more control in the stable case.
Okay, thank you. So now I would like to ask a question about a different subjects. The pattern formation. Can you go to slide 17?
Yes, I will go outside of this. This?
Yes, perfect. So what is very striking about this image, and also if you look at the image in 3D, the optical textures that you have produced, which is very impressive. Okay, if you go back to the previous one, what is nice is that looking just like that, let's say the 1D spatial temporal diagram and the 2D diagram, they look very similar.
Yes.
So do you have an explanation for that?
Well, since they are patterned, you will expect that most of the dynamics will be created by, in the case of the two-dimensional case, most of the weird dynamics or the non-purely advective dynamics will be created or related to the creation of defects in the texture, this location. So you have that, you try to connect two wavelengths with one wavelength, so you create a defect. And that interaction mechanism will give rise to the complexity. So indeed, okay, there is an analogy, but indeed the two-dimensional case looks more complex than the one-dimensional case.
So did you measure that?
Yes, indeed, in the one-dimensional case, there were no significant regions with positive Lyapunov exponent. There were like isolated points, but the largest Lyapunov exponent wasn't very positive, it was close to 0. So for example, in this one, it's marginally positive, so it's not really convincing. Indeed, for example, I will say that the main difference, I will focus in the difference because I think it's clear. The main difference, it's because in the two-dimensional case, you have effectively creation of these locations, which has they cross this transversal line and give rise to dynamics that is more rich and more complex. In the one-dimensional case, yes, we have more complexity. In the quasi-one-dimensional case, we have more complexity, but it's, let's say, namely less complex than this one. And also we have this, that the similarities are, okay, they are similar by look, but really if we measure some quantity related to the complexity of dynamic, for example, the largest Lyapunov exponent, they are very different. The one-dimensional case and two-dimensional case are very different, and that's why in this study we focus on the purely two-dimensional case. We discussed it very briefly, the one-dimensional case. At that time, we couldn't really understood why, and we believe that is related to the proposal mechanism that we discussed here. which is a one-dimensional model that has complexity. But if we consider a two-dimensional model in which we have displacement, indeed the kind of complexity is different. We observe different textures, different results, and we are working in that direction on linking in one direction in linking the liquid crystal light bulb experiment with the model, but also the two-dimensional case phenomenologically is different. And we claim that is because of this emergence of this location that can travel up and down, which in the one-dimensional case they can't.
So concerning this very particular slide that you show, where in fact the mechanism for complexity is kind of spatial delayed feedback. So you have translational feedback if you want. So it's non-local coupling.
Yes.
How would you describe that as generic or non-generic? So how would you, what genericity would you find in this kind of non-local coupling? Would you say that it's something that we may find in many other systems, or that it's very particular to your system?
Well, if we at the beginning only focus in the spatial component, and we don't think very hard about the significance of the space, I will say that this is generic in the sense that it's related to misalignment. So we claim that any system with non-local coupling that has some sort of pattern formation, you will expect that by increasing the misalignment, the optical misalignment, for example, in the feedback, you will expect to observe some increasing complexity by moving forward further and further the feedback. So I will say that it's robot in that direction, that indeed you have a misalignment induced dynamics. But in the other side, the space, the only thing that has a particular in this equation is that it appears only in this symmetric operator. It's quadratic, order 2 and order 4 in space. So, for example, all the results in this case couldn't be directly translated for the temporal case, because in the temporal case you have the that you have only forward interaction, not this symmetric interaction. But I will say that as a general mechanism, as a general framework there are some conclusions that are applied. For example, I will expect that for feedback loops that goes larger, I will, for some systems under certain condition, I will say that the complexity will increase, which is kind of expected, because if you have temporal feedback, you increase the dimensionality of the system, because now it's you have that it interact with the past. So I will say that as a framework is useful, but I wouldn't be really sure, or I will have to check from case to case, because this kind of fourth order temporal operator, I'm not really sure in which contexts are present. There might be, but I don't know any. No.
Okay, if we are thinking also in terms of experiment, so okay, so what you show is that small misalignment can have dramatic consequences in your system. So my question would be, how make you sure that you are perfectly aligned in your feedback in terms of rotation and in terms of translation?
I will say that the only significant mechanism that you have is, or the only thing that you have in your favor, is that since your experiment has a finite size, you will have pinning, because I'm thinking in experiment with characteristic wavelength. So since your experiment is finite, you will have pinning, and you might say that in any situation where you have a no apparent dynamic is because you are in the pinning region, so it's good enough. I will say that it's from an experimental point of view, you have to define the good enough, and the good enough is given by when you are inside of the pinning region where you don't observe any advection. So I will say that the size of the finite size of the experimental realization in this particular case plays in favor, because otherwise it will be completely impossible to align.
On the other hand, what you see here on this slide is that, for instance, even if you have a small misalignment, but below, for instance, 1.5, your homogeneous steady state is still stable, and so you have a region where, in fact, it does not change a lot if you are a little bit misaligned. No.
Okay, this direction of the misalignment,
yes,
is the direction of the voltage, let's say, of the mean bifurcation parameter, the mechanism that makes patterns emerge. And indeed, for example, if you cross this curve, so you have a small misalignment, you will only observe in an infinite system that you have stationary patterns and they start to advect. In a finite system, you will not see that, because spinning, I mean, it will shift the curve, as we saw previously in the case of the normal fronts. And indeed, the complexity is only relevant, I will say, in the case of when you have a significant misalignment. In this region, we don't really see any dramatic effect. So this also could give us some insight of what does misalignment means, or how to link optical misalignment, optical real experimental misalignment, with this simple model. If you have some mechanism of tracking these curves, these boundaries, in particular this boundary, from homogeneous steady state to complex states, yes, I will expect that will give some insight of how to link an experiment and the misalignment in an experiment with this model.
Okay, I would like to finish by a small question, the last part, which I think also is very interesting. As Stefania said, I would like to complement a little bit her question about the possible applications of this SLM, which is controlled by optical means. So, okay, two things. I would like just to, because you mentioned this application, and what would be would you gain something in terms of speed, for instance, of response with respect to standard light valve?
I would say that you don't really, because phototropic and thermotropic processes are somewhat slower than, for example, the electric effects, when you can in this case, the speed of the rotation, or the speed of the creation of the disorder, is related to the elasticity of the system mostly. But in the electric case, it's related to the competition between the elasticity and the electric field. So you can just put a very strong electric field, which could create a very strong change. If you have, for example, a binary mask, and if you are not interested in the intermediate states. So I wouldn't really expect to surpass electrical means with that. I will say that the main advantage is that a purely optical valve could operate in situations where, for example, it's not possible to apply to use electrodes. For example, if your system is very sensitive to fields, or for some reason you don't really have access or the possibility of implementing a capacitor for any given reason, because that will distort any result, or because the electronic could be cumbersome. By creating this transition by purely optical means could be an advantage. An additional advantage is that electrically operated liquid crystal devices has this part that they need wires, and wires can be also, from the mechanical point of view, a difficulty that for some reason you don't want to have in your system. So that's also a possibility that could help an experimental setup that where wires are not really a possibility. So I will say that the main gains of this setup will be in the direction of where the electrical devices are not really convenient because of the wiring or because the electronics and electric fields could create some disruption in the general environment in which you are working.
And I notice also that in this configuration, you don't study the effect of feedback. And this reminds me of some well-known results obtained in sodium vapors by many groups, particularly the group of Wolfhard-Lang, who just put a single mirror and put a single feedback mirror in a thin slide of active medium, and you get a lot of pattern formation of different patterns. So, do you think could be interesting to do also in this kind of light bulb? Well, not light bulb, but optical light bulb.
Yes. Yeah, that will be interesting. Indeed, we will expect to observe some sort of Talbot effect. It has been reported in dye-doped liquid crystals. This feedback, and if it's well aligned, you will have this hexagon formation, and a small misalignment will transition to a pattern formation. Indeed, from an historical point of view, that was the starting point in which inspired the progression of the group towards a dye-doped liquid crystal. But in the road towards those studies, we obtained several other things that we noticed that the community didn't understand very well. For example, the spatial properties of how the isotropic texture invades the birefringent state when the spatial properties of the medium are relevant. Because, okay, in the thermotropic case, it's really difficult to obtain, for example, a hot spot. It's very difficult. It's also very dangerous. For example, you can get closer with a hot stick, but that's also not very convenient to the optics. For example, if you are looking with a microscope objective, it's not really good to get any closer with something hot. So these spatial properties are really unique, or these very good controlled spatial properties are a very unique characteristic of light phototropic transition. So indeed, we started wanting to study this Talbot light effect, but in the road to get there, we got distracted with all these other results and topics.
You had everything in mind, of course. Okay, so I think I will stop here because already I had a lot of questions. So I would like to thank you for your answers, for your again congratulate you for your nice work, and I will leave the other members of the jury asking questions. So thank you.
Thanks.
Thank you very much, Sylvain. Mario?
Yes, thank you, Alejandro. Gregorio, first of all, I want to congratulate you. You did a really good job during all these years, and I'm very happy. I will ask you a few questions because some of them have already been made. But can you please explain a little bit about the mechanism of roll waves creation that you observed?
Okay, regarding a concrete mechanism, we haven't advanced toward that. These studies with the complexity in the measurement of the largest diagonal exponent and the proportional extreme events were mostly descriptive. We were focused mostly on describing this weird, complex, and rich texture that we were obtaining in the liquid crystal light bulb. So regarding a mechanism, as I commented previously, we were tuning the voltage, the external drive. So the external drive, regarding the mechanism that the general mechanism that we are proposing, is related to in some way to not only with epsilon, but it's one of the main parameters. So of course we are well above the transition. This model is mostly focusing on describing when you are in the threshold or you are just above the regions where you have patterns and you start to obtain more complex things, more complex dynamics. But regarding a mechanism, I will say that the main mechanism will be transitioning from these different regions. These are in the onset of the starting of the complexity. So there might be several different regions for stronger epsilon and significant delta. So since we started with a homogeneous steady state with frozen rows, I will say that we were most probably around this region. And when we increased the voltage, we started to do some curves along this line. For example, we observed that the complexity is not monotonic. For very strong voltage, we return to stationary patterns. Sorry. So I will say that the experimental curves that you will follow in these diagrams are very complex curves where maybe it's folded and going back. But I will say that, and this is a proposal that we are trying to verify, is that every time that you cross one of these separation between these complex regions, you will have some bursting in the amount of in the proportion of extreme events. So that will be my bet as a general mechanism. You transition from something complex to something of other kind of complexity.
Like changing a attractor.
Yeah, for example, changing the attractor, as in, for example, regarding that, if we plot the recursive,
yeah.
For example, here, you can do this mechanism, this recursion, where you start to plotting the intensity at certain point and compare it with successive times. And you will see that, for example, the effective attractor in this retardation map will correspond to a fixed point where you have stationary patterns. In this region, we observed something which has a torus shape with some noise. And in the fully chaotic region, we have this really complex but not noisy attractor where it's multiple foldings in several directions.
Yeah.
And I will expect that, for example, these regions where we observe a very strong increment in the extreme events correspond to the situation where the system is trying to going from this strain attractor to this torus. So maybe the system is most of the time around this the torus that is developed right here, but it does a very strong excursion, which is related as a general mechanism of when you're in the transition of something complex to something of other kind of complexity.
Yes. And do you think that the crisis provoked by the absence of light has something to do with that? You know, the green curve that you are showing there.
Yes, of course. This corresponds to the average light intensity in
the value.
In the full texture. So due to the destructive interference, we have that the light intensity is expected in an homogeneous texture to decrease a lot. And indeed, we have that the average values in this region decreases a lot. But we have this strong excursion toward some very bright spots, some very bright and isolated spots that appear and disappear. Of course, I think they have a mechanism, but for me, it's not really that clear, because this dark region means that we are in a situation where the feedback, effective feedback, is very weak. So you will expect maybe some tamer texture, but at the end, what you obtain, it's okay, it's tamer, but it does this strong excursion. So it's not really that clear which is the role, because for very low intensity, I will expect a purely capacitive liquid crystal device, as described in this slide.
Yeah.
But still, the feedback plays a role in creating very bright spots. So I will say it has a role, it plays for sure a role, but I wouldn't be sure to say which is the precise role, besides this saying that it makes the experimental situation closer to the most basic liquid crystal device.
Okay. Well, thank you. I have another question about the cells in photoisomerization. Do you know if the anchoring plays a role, or what kind of role plays the anchoring in the photoisomerization pattern formation?
Yes, the anchoring plays a very important role. Indeed, for example, in the basic experiment that I show, this is performing planar anchoring. So we have that the anchoring in both layers is parallel.
Okay.
But if you repeat the same experiment now in twisted anchoring, and slightly different concentration, you observe this other result, as you can see in this cartoon representation. So indeed, it plays a very strong role. The possible explanation is that the most unstable mode, in the case, for example, of planar anchoring, as I described it, is that the liquid crystal just flips. So the elasticity is mostly related to this bending mode. But when you have the cross anchoring condition, the liquid crystal inside performs a homogeneous twist. So now the twist mode is open. It's an active route, because now the minimization of the system is not this planar case, but this twist case. So that changes the effective elastic constants of the system. And by changing that, I will expect, for example, changing the parameters regarding this model, or the reduced parameter in this more complex model, which are related to the scaling in this equation. So indeed, it plays a very significant role. It changed the texture that you obtain. But we haven't explored, because of course you have that there must be a soft connection between this planar and planar twist. You have the intermediate states.
Yes.
So there must be a transition between this finger-like texture and the homogeneous front propagating like a circular spot. So that's also a direction of research that it's left open in my research, which is the transition, the angle in the anchoring, which effectively triggers this different phenomenology and this control between these three main phenomenology that we observe: this ring propagation, this finger propagation, and this homogeneous spot. And I will say that it's really a balance. It's totally controlled by the angle between the two anchoring planes.
Okay. And did you try with the homotropic anchoring or not?
In the case of homotropic anchoring, is quite tricky because in the case of homotropic anchoring, you have that the texture is dark when you see under cross polarization. The texture is dark, as we saw in this video. So here, for example, we have due to the electrical interaction, we see an effective homotropic texture, which is dark. And the isotropic texture under cross polarization is also dark. So it will be somewhat hard to observe a difference. The only technique that you could use is to try to detect the boundary between the two, because since, okay, both are dark, but they have different birefringence angle. Sorry, the birefringence speed of propagation of light. Birefringence, refractive index. Sorry, I have a slip. So this difference in the refractive index has a consequence that two mediums with different refractive index touching are separated by a dark line. So that will be a mechanism, but it's very hard to detect in this case, because the difference in the refractive index is not that high. So no, we haven't tried because experimental is complex, and we will need to expand towards different kind of microscopy device.
Yeah.
For example, differential microscopy.
Okay. Well, thank you. And at the last, I remember that you show some structures, photoisomerizate, that were almost permanent.
Yes.
What happened to those structures when you apply an external force to them?
Like electric field or magnetic field?
Like an electric or magnetic field, yeah. Can you destroy them or change them, or are quite permanent?
Okay, the permanent texture that you are referring, I'm not sure if I put an slide.
For example, the patterns that you show in your...
No, but it's in the manuscript. I don't have it open now, but okay. So, okay, when you
just
do...
Yes.
When you do photosolidification, in the case of methyl red, and after repeating and repeating the realizations, you observe a degradation in the anchoring. Indeed, it got with permanent marks. The anchoring suffers an aging. I wouldn't say it's destroyed, but it changes.
Okay.
And this change is very strong because it's a very strong dielectric effect between the polymer that is rubbed and the molecules. So the electric and magnetic fields effects are mostly in the bulk, and this anchoring is mostly in the boundaries. So I'm not sure if there is an effect.
Okay.
Besides just that, if you change the boundary conditions, of course you change the bulk solution. But I wouldn't expect I haven't tried, but I wouldn't really expect some effects of external field over the anchoring unless you apply very strong fields. But
yeah, sure, of course.
But for reasonable fields, no, I wouldn't expect any effect in this aging process.
Okay, well, thank you so much, Gregorio, and let me congratulate you again. You did a really good job, as I told you before. And for my part, it's everything. Thank you.
Thanks, Mario.
Thank you, Mario. I guess it's my turn before the advisor. First of all, Gregorio, thank you very much. I think it was a very good presentation. I also congratulate you on the number of topics that you cover in your PhD thesis. It was quite extensive, and the number of publications. So congratulations on that. I have a few a few comments actually on some of these. Actually, maybe we can stay on this transparency.
Yes.
I was wondering if you increase the density of your mnemonic particles, right? Is there a possibility of going from a elastic to a plastic transition, something more complicated than the theta, the z square term?
Indeed, this is derived from what is called the Leslie elastic model, and this is an approximation of an approximation.
Sure.
If you consider, indeed, it's an approximation of an approximation of an approximation, because we consider all the possibility of the deformations, but always in an elastic framework and not real plastic deformations are considered. It's not really easy to consider permanent deformations in that could give rise to very non-linear effects in the elasticity. Because since
I was wondering, Gregorio, I was wondering when they start bothering each other.
Indeed, that kind of deformation should be considered. That since it's a very viscous, the response time is not very fast, the relaxed energy very fast. So I'm not sure if that kind of very violent consideration could be achieved. I haven't seen from an experimental point of view that should be considered be inside of the general Leslie model, but from an experimental point of view, I haven't seen it, and I'm not sure which, because at the end, the mechanism to create these very strong deformations will be applying very strong external fields, which deform the system permanently. Okay, for very strong, for example, electric fields, you have that the system becomes conductive, in that it gets burned. By creating this video, I burned this liquid crystal cell because I wanted this process to be very fast. So yes, it got permanently damaged. So I will say that no, it's at least experimentally is not possible, because from an electrical point of view, it gets burned before we observe permanent plastic deformations.
Okay. Can you go a little higher, a couple of transparencies up? Before, right? When you talk about the dielectric constant.
Okay,
probably.
Like this or
either one. Yeah, that's fine.
Okay.
I was wondering, or even maybe the previous one actually. I was wondering, just for my understanding, when you put a magnetic field here, how you're gonna change this? So I will figure. What is the magnetic field is doing here? Because it's breaking here some, I will figure, my intuition is on plasma, so you will make it more tensorial, higher order, or something like that, right? Because you're going to mix like two tensors here.
Yes, indeed. I mean, first, this differential volume that we represent as rho in this transparency, sure, by linking this molecule, this individual molecule, to this rho, is not good, because the liquid crystal, they interact, and this is effectively a differential volume that contains several molecules. And the collective effects, it has no preferred direction.
But when you impose a magnetic field, the guy want to rotate in a certain way, I guess, right?
Oh, yeah. If you put a magnetic field, it's mostly the same as an electric field, but you have to replace the electric susceptibility with the magnetic susceptibility. Of course, for example, you can have materials with positive electrical anisotropy, but negative magnetic anisotropy. So you can have a more play. Indeed, for example, in this case, the boundary conditions are homotropic, so the molecules are, this is the electrodes, this is the direction of the molecules. You apply a magnetic field that is mostly perpendicular. And the material has negative dielectric anisotropy, so the molecules, the torque, it's not like the electric field that try to align, but this one try to misalign. And this is the origin of these vortices. So indeed, basically in the case of the magnetic, for moderate magnetic fields, you will obtain that is the same analogy as in electric fields. Just you have to replace the electric and magnetic susceptibility correspondingly.
But I mean, I was thinking something combined, electric and magnetic, in the sense that if you put a constant magnetic field, you can think that as a tensorial effect. For example, when you have charged particles, if you put a magnetic field, it's like instead of having a dielectric constant that is isotropic, a dielectric tensor that is isotropic, you make it anisotropic. Like similar, what is an expression very similar to what you have on the transparency 5, in fact. So like the Sij is very similar to that. So I was wondering whether if you put a magnetic field, you can simulate it like something that will break your Sij in that second order tensor type, because it's like two tensors, one produced by the magnetic field and another one like this. And then you impose, suppose you put on your experimental setup, you put an external constant magnetic field. I was saying, but that's my, I guess you could actually confuse this, you can break this expression that you have for the Sij in that case. I'm trying to understand. I mean, I don't know a system, but I'm trying to figure it out. What will happen if you put an extra magnetic field?
Yes, I mean, if you put a magnetic field, for example, in the case of energy, the experimental results are basically the same. You have that the external magnetic field will interact through the magnetization of the system instead of the polarizability of the system. So you have a complete analogy between electric and magnetic fields, because okay, the electric fields at the end both are vectors applied over a medium that is highly anisotropic. So in the case of plasma, okay, you break this isotropic symmetry and create a polarization, but this medium is already anisotropic. So
the two anisotropies
like
will fight.
It inherits the anisotropy. It doesn't change really the forces. I mean, from the theory, you just have to change the polarizability for the corresponding magnetic analog, and you obtain mostly the same results. The only caution that you have to have is that this will not be the same for the electric case and the magnetic case, but the results will be the same. It will try to align or be orthogonal.
Yeah, but I wonder because I mean you could actually put P.dE and then you could do an M.dB, right? Two terms like that. But I wonder if because of the structure of these things, the M and P or the M and E will interact. There will be a cross term.
Indeed, they might. I'm not sure if I have seen results in that direction, but indeed, if you have both, they should start interacting because, okay, in the linear case, they will just compete in the energy, but
sure.
If you have a more non-linear case for stronger fields, you will start to having cross interaction where the system start to create movements and yes, indeed, but most of the liquid crystal operates at close to the linear regime or at most a Kerr regime. So in the case of electromagnetic field, so I haven't seen any study in that direction of the kind of complex behavior, most probably because you will need a very strong electric and magnetic fields, which are experimentally not easily achievable. So I will say that there might be some effect, but I wouldn't be sure, because in this case you have three effects. You have the anisotropy of the material, the polarizability of the material, the excitation of the material, the external magnetic fields, and the external electric fields. So it's already a very complex system. So I wouldn't venture to do any significant prediction in that direction.
Sure. Okay, excellent. You already answered the question about the velocity of the front. Could you go to transparency 17 or 18?
Okay.
It's interesting that we still use the word transparency. I guess that says something about our age. I was wondering, is it possible, I mean, what is your intuition? Because to characterize essentially the disorder in this system, you use the maximum Lyapunov exponent, spatial Lyapunov exponent, right? What if you use something like different, like a multifractal or something like that? Try to do the multifractal spectrum, how multifractal it is. Marcel is used to me making that question to almost everybody, but having a multifractal description of this. I was wondering.
I think it's a very interesting proposal, because first, from an experimental point of view or from a data analysis point of view, it's easier to compute than the largest Lyapunov exponent. The largest Lyapunov exponent is very hard to compute. It consumes a lot of resource. And going beyond the largest Lyapunov exponent is really hard from experimental. Even in numerical data, is very hard. Experimentally, it's more difficult. So yes, characterizing the complexity by using proxies, for example, this multifractality, is indeed a good proposal. For example, by using the bending, you could obtain some very strong insight. For example, in the bending, you can compute, for example,
I saw that, yeah. Exactly.
The Yorke-Kaplan dimension, and you could effectively obtain a proxy of the dimension, the fractal dimension of the attractor. And doing this is very easy compared to measure the largest Lyapunov exponent. There are works that have been done in that direction, not in experiment, but in fibers, thicker fibers. And indeed, it's a very good proxy, and I think it's, at least from an experimental point of view, is more promising because it has a very good fit. But it should be also reminded that the true characterization of complexity, of spatiotemporal complexity, is the largest Lyapunov exponent. So I bet that there are not a lot of cases where they uncouple, but the possibility of having a spatiotemporal complex from the Lyapunov exponent point of view, but not from the bending point of view, might be possible. So, because at the end, Yorke-Kaplan conjecture is a conjecture. So I will say that it has some value by measure the largest Lyapunov exponent, but from a practical point of view, I will say that everyone will be more inclined to measure the fractal characteristic of the attractor instead of the.
Yeah, because in this case it's very easy. You just calculate the correlation dimension.
Yeah.
Straightforward from there. Yeah.
Yes. No, I agree, and it has a very good agreement. But we were focusing mostly in the experimental, and also because it experimentally we haven't found any realization in optics, so that was the main motivation. Like, it was novel from the measurement of largest Lyapunov exponent in optics experiment, in a very spatially extended optical experiment.
Excellent. Could you go to page 22?
Yes.
Yeah, I was looking at the picture on the right, and it looks to me that you have a lot of coherent structures going around, and this actually will merge into the into the following question that I will ask you about the power laws. But what would be your intuition? Here, there's a lot of coherent structures that live forever, for a long time before they disappear, right? Especially when you have time dependency. I wonder how important these spatial structures are. Something that, for example, the time that the maximum Lyapunov exponent will not see very well, will have trouble seeing, is that this coherent structure, when you have those red dots, for example, they're probably controlling a lot of the dynamics. So there are techniques to do that, and I don't know how you feel about it, but you can actually try to find where those coherent structures that are moving around are. Usually in fluid, they will call it Lagrangian coherent structures, or plasmas also. So I was wondering if you have any intuition about that. Because usually when you have, for example, this will merge into the following question about turbulence. When you have turbulence, those coherent structures are very important in actually controlling what your power law is. And the deviation from Kolmogorov are usually because of these coherent structures that actually mix with the idea of multifractality. Multifractality, coherent structures, and changes in the power law of your fluctuations is very important. And this comes from my intuition of in plasmas, that usually in plasmas you have these two things. You have these coherent structures moving around. You have, for example, these fronts. In plasmas, it's very amazing. You have these step functions of magnetic field. The magnetic field changes more or less discontinuously. They're usually called current sheets. And you have these things propagating in the plasma. And on top of that, of course, you have all of these fluctuations. And there's a discussion today on how relevant each one of those two processes are. Essentially, the fluctuations, more or less the view of Kolmogorov, but also you have these fronts moving around, these current sheets. So that makes it a very interesting system. So I was wondering, here you have that. I mean, you have these fronts, right? And you have these coherent structures. So maybe you have, the interesting thing here is that maybe you have a control of the relative importance of those two things. So I don't know, what intuition can you bring out of this question? That would be interesting for me too.
Yes, I will say that by looking at the data, like by skimming through the data, one thing that one can see is that this creation of extreme events happens very frequently nearby the defects in the pattern. So you have the pattern, you have the defect, and typically nearby they appear these extreme events. So the emergence of these locations is more or less at random. I couldn't find, I mean, if you are far from the boundaries, it's more or less at random. But they live for a time. So they travel, they displace, so they drag with them this kind of high intensity in the illumination. So I will say that is some sort of a coherent mechanism that is not just a dissipation of energy towards small scales until it's relaxed. So yes, I will say that it's somewhat difficult because it's not really easy to control how long these defects will live. Mostly because in the complicated rundown, you see that in defect turbulences, just they emerge and disappear rapidly. So indeed, it's a good proposal, but I wouldn't be sure how to control that and the permanence time. Also, when we measured this, we had this problem that the cameras weren't really as fast as needed. The cameras that we were using were at around 20 or 30 frames per second recording. And the characteristics timescales of liquid crystal is in the order of milliseconds, 10 milliseconds. So you have a very difficult tracking things. It's not that easy to track things with that frame rate. Nowadays, we have better cameras with a faster acquiring time, faster acquiring frame rate, and also with more deep in the gray value, the acquiring data. So this also we have deep in the acquiring data of 2 to the power of 8. The cameras that we have currently are 2 to the power of 12. So indeed, I think there is some room to improve in that direction of tracking what is the effect of these structures that are permanent during a time, that drag with them the extreme events. But if we want to contrast it with something, I will say, okay, we can contrast it with our proposal model based on misalignment theory, on non-local coupling. But it will be somewhat difficult to relate, to use as a control parameter, because the creation and destruction of these defects is somewhat non-controllable. So,
but in essence, can you put 27?
Yes.
I was wondering if these 2 power laws that you have here somehow give you some intuition, or tell you about some intuition about the type of coherent structures that you see, how long they live, or how relevant are in your behavior, right? I know that the different regimes between turbulence and this STI regime, but I was wondering if these coherent structures are exactly what they control, the two that are, how they tell you about these 2 regimes, or these 2 power laws in essence.
Yes, you have this scale, which is very plain. Then you have this power law regime, which, okay, is somewhat related to turbulence, at least. I mean, even the number is suggestive, the -2.
You see that there's a difference between, I mean, pictorially, between the blue figure on top and the blue figure on the bottom.
Yes, yes.
The one on the bottom, it looks more like fully developed, right? And the other one is more concentrated on coherent structures. And interesting, you put the name differently. You say fully developed turbulence at the one on top instead of the one on the bottom, right?
Yes, I mean, both follow power law, so both are more or less on their scaling, more or less the same. I mean, you can scale. There is scaling connecting them. But yeah, this one is sharper in the power law. The number is more negative. So yes, in this case, we have you could say that we have turbulence, at least in this regime, but we must also consider that there are resolution problems. For example, you have some sort of Nyquist limits. You're in this region, you're getting closer to the Nyquist limits of resolution of data. So I wouldn't say any claim around this. So basically what you can observe is this structure where, okay, due to the, since we're using the power law, the points get more sparse in this region and more concentrated toward this part. So I wouldn't do any very strong claim comparing these two. Because in this numerical case, okay, you have better resolution and you don't have this multitude of accumulating problems relating to the camera, the acquiring time, and so on. In the numerical simulation, you have all the data. So the comparison is not really clear, at least for me. Beyond that, there is some scaling connecting both, because both are power law.
Okay. And can you put the last one? Can you put figure 42?
Yes.
That thing looks like an explosion, right? Do you see something like Kelvin Helmholtz on the edge, away from your fingers? There.
Okay,
I know it's very dissipative, so you shouldn't see very much, but I was wondering.
Yes, but I mean, it's somewhat okay. At least in the very beginning, you can see that this is suggestive. Because yes, it's very dissipative, but also the light injection is very strong. So it's not really clear that we are in the completely dissipative case where you don't have some sort of explosion or waves dragging matters outward. So at least it's suggestive in this part. Yet maybe it could be understood as explosion, but also when you are closing, this is very dissipative. So there might be, but we haven't studied in that direction. I think you will need a higher power density to really observe something like that, like matter being explosive. But in this regime, it looks more like a matter being transformed from the birefringent state, from the nematic state to the isotropic state, at least for me. But I will concede that yes, this first stage is very suggestive.
In the beginning, yeah, boom.
Yes, it's very suggestive, and it will be an interesting direction to move because basically you have this comparison between the proper time scale, the dissipative scale of the liquid crystal, and the driving that you are using in your system. So if you use a very strong laser or very concentrated laser, I will expect this to be, this outermost part to be more relevant. So there may be something there. It's an interesting proposal and question.
Do you see, Gregorio, can you control the velocity of the expansion?
If you increase the pump, yes, you can control up to a certain degree. There are, for lower pumping, you start to have no fingers, but more ring-like structure. So, but up to some degree, you can control the, I mean, here, for example, no, this is the wavelength. We didn't plot because it wasn't any particular configuration, but yes, the propagation speed, you have some degree of control with the light intensity. But also it changed the wavelength of the fingers, as you will expect, like in Subman-Taylor experiment, when you inject faster, you change the capillary number.
Sure.
So we change the fingers, so might be also that. But yes, you up to a certain degree, you have control over the propagation speed.
Yeah, it's a mixture between Raleigh-Taylor and Kelvin Helmholtz. Really cool.
Yes.
Okay.
Yeah, that could be the case.
Yeah. Thank you very much, Gregorio. And let me repeat it again. I think I congratulate you because you actually work on a lot of different topics, and it was quite extensive and very good, very well done. So congratulations. Marcel?
Thanks.
Okay, so also I'd like to congratulate to Gregorio for this, in my opinion, very outstanding thesis. I'm very happy for that. Even I'm very proud. Only want to mention that when Gregorio started working with me, he started to like a student, but very quickly, maybe after 1 or 2 years, he's responsible of the lab. So I'm very happy because Gregorio create different experiments, not only create different experiments, also he create different methods to analyze the data. So I'm very happy for the work of Gregorio. And as consequence of all this work, we have published around to 12 papers. So I'm very happy for that. In my opinion, this is very outstanding for a PhD student. So this is a manifestation of the maturity of Gregorio. Also, Gregorio is very brilliant in several ways. So I'm very happy for that. So maybe when Gregorio left the lab, really I miss him. So Gregorio, thank you anyway for all this. So all the people have a lot of questions for you. So I think you reply more or less very well. So only have one question. So my question is only that you have have a lot of result. So in your opinion, which is your more important contribution and why?
Okay, thanks, Marcel, for the commentary. I will also miss the laboratory. I see it grow along with me. So, and the group and the people. So, yes, of course, thanks for all the mentoring. And regarding your question, I will say that the main contribution is studying and analyzing what is the effects of the interaction of light with matter and matter with light simultaneously. You have that there are multiple results and multiple studies focusing on what happens when you apply, for example, light to a system and what change it produces in the system. And in other part, you have several studies pointing, okay, how can I use this material to control the properties of light? But I will say that my favorite topic during this thesis and why I was able to cover so much topics was because I got interested in how can I make matter interact with light in an active way, in a syncretic way, no as an isolated part, not as an stimuli based, but a system that is constantly interacted with itself. So I will say that my main contribution and my favorite topic is how can I make a system interact with itself. In the case of what happens when the liquid crystal light value interacts with itself, we see the emergence of fronts, of these pattern textures. So we have this this kind of a framework, which is the one that motivates me most. How can I use light to interact with matter, and how not only how can I use light to interact with matter and matter to interact with light, but how can I make matter interact with itself through light, or how can I make light interact with itself through matter? I will say that is the highlight of my results. That is the thread that connects them all are about this interaction.
Okay, thank you very much, and congratulations again.
Yeah, thank you very much to everybody. Estefania, Mario, Sylvain, thank you very much for your time. We need to meet for a few minutes by ourselves, right?
So I stopped to the live 1 second also.